Hello everyone, welcome back to our second podcast in our channel TV Ki Padhai. And today again, I am third year student, chemical engineering, Dhananjay Tiwari, and with us we have Vikas Yadav. He is also a third year chemical engineering student. And today again we are going to discuss about packed bed. So Vikas, in our previous podcast we have already discussed what is a packed bed column. And also discuss how to find out friction factor in a packed bed column. But there are many processes occurring in the packed bed column, not only that the fluid is flowing through the column and we are finding friction factor. There are also other processes like heat transfer, mass transfer. So this today's topic which we are going to discuss, heat transfer coefficient in a packed bed column. Heat transfer is a very important process not only in packed bed but in every area of the chemical engineering. So today we are going to discuss about heat transfer. So Vikas, what role heat transfer plays in a packed bed column?
So basically, heat transfer plays a crucial role in the processes, like maintaining the reaction temperature. Some reactions are of exothermic or endothermic.
Yes.
We have to maintain the specific reaction for completing the. We have to maintain the specific temperature for completing the reaction. So heat transfer plays a very huge role. Also, for cooling purposes, we should know about the heat transfer coefficient also. And there are also processes like phase transformations, like evaporation occurs. So for that, we have to be a specific temperature particularly. So we should know about that heat transfer coefficient so that we can easily calculate it.
Means what is the efficiency of transfer of heat
Yes.
between the solid packing material and the fluid flowing. So in the same regard, I have my second question, because heat transfer is taking place in a packed bed column between fluid and packing material, we all know. But we want to know how it is happening. What are the key mechanisms? How the heat transfer is actually happening inside the column?
Basically, as we had already studied in heat transfer, like three things are there, like conduction, convection, and radiation. All of three are taking place in the packed bed column, but the radiation, the third one, is very less. So we are neglecting that radiation. So basically, two are the major transfer taking place. One is conduction, and second is convection. Primarily, convection, that is occurring between fluid and the packing surface. So what is happening? That fluid and particle surface, there is a transfer of heat via convection mechanism.
When the phases are different. No?
Yes. So different phases we having convection heat of transfer. Secondly, the conduction. Conduction are occurring within the packing through the film. So in this via this we are having conduction heat of transfer. So these are the major mechanism of heat transfer in packed bed.
So the majorly heat transfer is through
Conduction and convection.
And in that also the convection is the major part. I think.
Yes.
So the my next question will be, like, in packed bed column there may be very different kinds of packing materials, their shapes, their geometries, maybe like we can have cubes, we can have cylindrical, spherical packing material. So how does a packing material, its geometry, its shape influence the heat transfer?
Basically, we are putting that packing material inside the column to increase the surface area. Also, we want least possible void area, because the more area that is present in the column, so basically we are hoping toward the larger surface area. So there are various shapes like cylindrical, spherical, rings. Mostly we are using cylindrical surfaces and dashi rings all in all. So these shapes vary in their area. So we have to choose a specific packing material so that we can have that definite area. Also, void fraction plays a major role. Like if you are using a sphere, so the void fraction might be something, and if you are using the cylinder, then void fraction will be different. So for every process, we should determine that what we are required, like how much void area or surface area if we are required, so we can choose that material as well.
So the main thing that you are trying to say is that the surface area, heat transfer area must be the larger the heat transfer area, better the
Heat.
shape and geometry.
Yes.
Better will be the heat conduction.
The higher surface area and better the wetting improve the coefficient of heat transfer.
Oh, so wetting should also be more.
More.
Okay. So there are many parameters in heat transfer like Reynolds number and the velocity of the fluid, what is the temperature difference, and what is the heat transfer area, and what type of fluid is flowing. So my question is ki, what are the there are various parameters. What are the main parameters that affect the heat transfer?
Yes, that's a good question. Major parameters that are influencing the heat transfer. First one is the fluid velocity. Fluid velocity plays an important role. We cannot take the velocity as greater because the resistance time will be very low, so conversion will be low. So fluid velocity is the first parameter. Second is packing type and size, as we had discussed. And packing materials plays a very vital role in that column. Third one is temperature difference. Inlet temperature and the outlet temperature. The difference in the temperature also plays about that heat transfer coefficient, because from the Newton's law of cooling, we
More
know
the
that
temperature difference,
yes,
more the heat transfer.
yes. So and then physical properties are also there, like viscosity, density, and the flow design. As we have already discussed in the last question, that majorly in the industrial applications there are laminar, not laminar, turbulent and the transient phase. So design should also be known, because from the design we can have different formulas for calculating the heat transfer coefficient.
So my next question is on that only. The most important factor in the heat transfer is area. Definitely it is area, but heat transfer coefficient is also a very important factor, and that is what our main topic is, how we can calculate heat transfer coefficient in packed bed column. So I would like to ask you, what are the methods that we can find heat transfer coefficient?
So basically, for calculating the heat transfer coefficient, we should know that Newton's law of cooling. From Newton's law of cooling, if you have the heat flux and area, you know about the packed bed column and the temperature difference, so you can easily calculate the heat transfer coefficient by the formula H equals to Q upon A delta T, basic formula. So you can get heat transfer coefficient from that.
But many a times, like temperature difference is not given, like temperature difference is not constant, it is varying, and like area is not given. So in that case, what we can do?
We had studied in transfer phenomena that there are various empirical relations like Prandtl number, Schmidt number, and some analogies like Chilton-Colburn analogy. So from that dimensionless numbers, we can easily calculate the required parameters like H, K, Cp and everything. So from there, use the values of this numbers and get the coefficient and put in the formula. You can easily get the heat transfer coefficient.
Okay, so this is the very important thing to note down to our students and viewers. So we have talked about the packed bed and heat transfer inside the packed bed, but are we really seeing this thing in industries? Are we really using the packed bed columns, and are these things relevant, or we are only studying these in books?
No. The packed bed column are really very much used in the industry. There are major roles where packed bed column is used. Like separation also we had also studied. But basically, the industrial applications are reactor design. If we are doing a reaction, so we have to design a reactor. For that, we should have some basic parameters like temperature, pressure, and so we have to design a reactor. So first one is the reactor design. Second is distillation and absorption, as we had discussed in podcast one. Third one is heat exchanger. Somehow heat exchanger also majorly designed on that packed bed column. Then optimization is also important because there is a lot of energy loss. So we have to optimize the energy. So for that also we are using that packed bed column. So these are the fundamental parameters where we are using the packed bed column in industrial applications.
So we've talked a lot about heat transfer coefficient inside a packed bed column, and there are many important things to note down, like what is the importance of heat transfer coefficient, and how to determine it, methods, and the parameters affecting it, and majorly that if you are going to become a chemical engineer, you are definitely going to see packed bed columns, or you will definitely design reactors.
Yes, yes. In process engineer also designs these things.
If you become a process engineer, you will design reactor, then all this knowledge would be required, and that's why you should learn how to find heat transfer coefficient in packed bed columns. So thank you, Vikas, and thank you everyone. So now let's do a numerical to understand better how to calculate heat transfer coefficient in packed beds.
Thank you.
Thank you.
Yeah. So already we had discussed that friction factor question. So here we are with heat transfer question. So the question says, hope you have noted the question. So let's read the question. A packed bed column of lead shot with ds equals to 1.6 mm diameter, porosity is given as 0.38. The lead shot are housed inside a pipe diameter of d equals to 154 and L equals to 915 mm. What is given that we have a packed bed column which diameter is given and length is given, and the packed material that is of lead shot with diameter is 1.6 mm and porosity is given. So what is happening? Nitrogen gas at an average pressure P equals to 2 atmospheric and average temperature 200 Kelvin flow through the packed bed with mass flow rate this 0.080 kg per second. Determine the heat transfer coefficient for the packed bed column. Given values are mu of N2 at this given temperature and pressure is 12.95 into 10 to the minus 6 Pascal second. Prandtl number is given as 0.72567. Cp value of N2 is given at 1.047 into 10 to the power 3 joule per kg per Kelvin, and Chilton-Colburn factor for heat transfer is 0.23 Re to the power 0.3. So let's draw the figure of the diagram. As given in question, a packed bed with given diameter is 154 mm and length of this packed bed is 915 mm. Lead particles so this is a diagram. Lead particles diameter. Here we are giving N2 gas, pressure 2 atmospheric and temperature equals to 200 Kelvin. So let's solve the question. Now we will see the solution of this question. So first we will calculate the Reynolds number. So let's write the formula. Re is given as dP into G 1 minus and into mu of psi. So dP is diameter of particle, which was given. G is mass flow rate per unit area. G can be calculated as G equals to mass flow rate upon cross sectional area of bed. Size is particle shape factor. Particle shape factor we know as for spherical particles is 1 and for cylindrical particle it is 0.92. Psi equals to 1 for spheres and psi equals to 0.92 for cylinder. dP is given as 1.6 into 10 to the power minus 3 meters. G can be calculated from that given formula. Mass flow rate was given as 0.080 and area of cylinder, that packed bed, can be calculated as pi by 4 into 0.154 square, which results into 4.295 kg meter square second. We can check from dimensions also that flow rate upon area. So flow rate kg per second upon area. So dimensionally it is also correct. So viscosity of that N2 at given pressure and temperature, that was 200 degree Kelvin temperature and pressure to atmospheric, was given as mu 12.95 into 10 to the power minus 6 Pascal second, and this was also given as 0.38. So we will be putting all these values to Reynolds number formula and getting the Reynolds number. So let's just erase this. You can note down these values which we had calculated. We will assuming the lead particle is spherical, so that psi value for that will be 1. So let's put all these values in this formula. 1.6 into 10 to the power minus 3, 4.295 we calculated, 1 minus 0.38 into 12.95 into 10 to the power minus 6 into 1, which results into 855.89. This is the Reynolds number we are getting from the formula. So this is the laminar region. Let's proceed further. Chilton-Colburn for heat transfer was given as this from the formula 0.23 RE to the power 0.3. That put all these values 0.23 into RE यहाँ से लेंगे 855.89 to the power 0.3, which you will calculate and will be 1.7436. Let's take as this 1. So hope you note down this. Let's proceed further. We had also studied the Chilton-Colburn analogy. So from that analogy, we are picking up a formula which is JH equals to Stanton number into Prandtl number to the power 2 by 3. First, this is we got from that Chilton-Colburn factor for heat transfer. So putting all these numbers formula, and we get standard number is H upon rho V Cp, and Prandtl number is Cp mu by K to the power 2 by 3. So rho and V is not given, so we will use G. G already we had calculated. The formula turns out H upon GCp into Cp mu upon K to the power 2 by 3. So as given in question, Prandtl number was 0.72567. Cp was given as 1.047 into 10 to the power 3 joule per kg Kelvin, that is of SI unit. And JH we calculate as H upon G Cp into Cp mu upon K to the power 2 by 3. We will put all these values. So we will be getting JH is H upon 4.295 into 1.047 into 10 to the power 3 into we will calculate by putting the value of Cp, mu and K. We will get a Prandtl number. Prandtl number turns out to be also already Prandtl number it is given 0.72567 to the power 2 by 3. So JH turn out to be JH H into 1.795 into 10 to the power minus 4. Let this equation as our equation 2. So we will equate equation 1 and 2, and from there we will calculate the value of H. So let's erase this. Earlier we had calculated that JH equals to 1.7436 as equation 1. So comparing equation 1 and 2, comparing equation 1 and 2, we get H into 1.795 into 10 to the power minus 4 equals to 1.7436. H equals to 1.7436 upon 1.795 into 10 to the power minus 4. So we will be getting H equals to 9713.65 watt per meter square Kelvin. So heat transfer coefficient turns out to be 9713.65 watt per meter per Kelvin. So we had calculated heat transfer coefficient for this question. That's all that question. Thank you.